Welcome to problem solving session for the course Linear Algebra. I am Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss syllabus problems related to syllabus from week 10, that is problems related to linear transformation, matrix of linear transformation, and matrix of linear transformation with respect to different bases. So let us start with our first problem. So, yeah. That if A1 to AD in M and K is a K basis of M and K if and only if A1 transpose. So this is A1 transpose, okay? A1 transpose, I will specify that. AD transpose is a basis of M and K. So this is our first question. So let us try to prove this. So it is already given that A1 to AD is a K basis of M and K. So we do not have to check that this is a basis for our M and K. And I hope, and so let me just write this, where this AT denotes the transpose of matrix AI, okay? And this M and K is all n cross n matrices over K, that is entries are from K, okay? And I hope, let me check if I am audible. Hello? Yeah. So, yeah, so we have to check that if given set of matrix forms a basis for vector space of matrices, then the transpose of those matrices will also form a basis for our vector space of matrices. That's what we want to prove. Okay, so let us start with the proof. So, and first thing, note that this MNK is n square dimensional vector space, okay? And I hope the standard basis with standard basis often denoted by Aij, where Aij such that Eij is a matrix such that Aij how to write this? Is that Eijth entry is 1, okay? So it is such that 0 if is equal to Aij is such that Aij is equal to 1 and, or let me write Aij is equal to 1 and how to write this? Eij such that suppose St, where such that Ast is equal to 1 if S is equal to I and J is equal to, T is equal to J and 0 otherwise. So it is like E11 is just 1 at the 1 entry. Okay, so let's see. Okay, and it's 0 otherwise. Okay, so this is how these matrices are. So this is standard basis. Okay, so this is n square dimensional vector space. So here D, which they have mentioned, is actually n square. So note that. So the what I wanted to say here is that note that uh, D mentioned in this question, uh, in the question is n square. But that we do not actually need that D being n squared to prove this statement. So what they are saying is that if A1 to AD is basis for vector space of matrices, then the transpose will also form a basis. So let us start with this. So what we do is we do it some using some different kind of method. So suppose we define this transformation. Let us define T from MNK to MNK. Okay. And what we have then such that this A goes to A transpose. Okay, this is my map. So now what I will try to do is I will prove that the set which is linearly independent. So this becomes bijection, and then the basis will be mapped to basis. That is what our idea is. Okay, I mean this is isomorphism. So since A1 to AD is a basis of MNK, then okay, then this then these matrices then these matrices are linearly independent. Yeah, and so so suppose if A1 transpose to AD transpose is not linearly independent, then uh, this we will have some CIs. There exists CI in K such that this summation CIA transpose I from 1 to D, because we have D many elements here, this will be 0. Okay, and so then since this T A going to A transpose is isomorphism, then when we apply T to this, then T of this summation I from 1 to D CIA power T will be 0, right? I mean 0 anyway goes to 0, but so this implies that this summation I from 1 to D Ci AI transpose, whole transpose, okay, is 0. And then this will imply summation I from 1 to d. Ci is a coefficient anyway, it's a constant, so we can take it out. And we get ai transpose is 0. And this will imply summation I from 1 to d. Ci ai transpose will become ai. This becomes 0. And once we have this is linear combination of ai's. This is, so this, if I call this star is a linear combination of ai's such that ai's which equals 0. Okay, but this a1 to ad is a basis of m and k, right? We have this. So this implies this each ci is 0 for all 1 less than equal to I less than equal to d. Right? This is what we will have. So this will imply the initial guess, this linear combination here. So this will imply, so therefore summation ci ai transpose I from 1 to d is equal to 0 implies ci is a 0 for all 1 less than equal to I less than equal to d. And hence we get that this A1 transpose to A2 transpose is a linearly independent set. And sorry, yeah, AD transpose. So from here itself, so what we had is we started with, first of all, we are using this, okay, that this transpose is a isomorphism. Okay, I mean, you can check that this, if you, I mean, we can spend time doing this, but so check that this is isomorphism. Check that uh, T is an isomorphism. I mean, it is easy to check because if something is 0, if something is mapped to 0, it means all the entries will be 0. And so what it is, what this is aij going to aji, right? And so if some matrix is mapped to 0, then all the aij's are 0, and then the corresponding reverse image will be 0 altogether. So that will give me the injectivity. And for surjectivity, if I choose any matrix, the corresponding, the transpose of that matrix itself will be, what I can say, will be pre-image. And if you do not want to do that, just understand that the T itself is a inverse of, inverse of this linear transformation. So T square is identity. So there are many ways to conclude a given map is isomorphism or not. One way to show that it is bijection, and so on. And the other way is obtain a linear transformation such that when we compose with it, we get identity from both the sides. So the T itself here acts as inverse of it under linear transformation. So T composed with T will give me identity. So this is all about T being an isomorphism because we used it. So this is essential part which we are using to prove this thing. So yeah, that's why I'm mentioning that. But apart from that, so this is what we got. That this is 0. And yes, so we have this, that this is linearly independent. And since A1 to AD was a basis of my vector space, and I have one another linearly independent set of the same cardinality, I can from here itself declare that this set A1 transpose to AD transpose is a basis for M and K. Okay, understand that. Let me write this, that Since A1 to AD is a basis of MNK, that is D is the dimension, K dimension, that is dimension of K, MNK is a D, and we have we have an a linearly independent set AD transpose of the cardinality of the size dimension K, Mn, K implies that this set A1, this transpose, this new set of cardinality D, which is linearly independent, forms a basis of MNK. Okay, so this is a statement that if dimension of dimension K of V is some n, then any linearly independent set of size or cardinality of size n will form a basis of V. Okay, and this n is definitely, I'm assuming, some finite number. So that is what I'm saying. So from here itself, we can declare that this A1 transpose to AD transpose is a basis of my vector space MNK. But we will also see that how this spans. So the linear independence is done. Now the spanning part. I'm just adding this to understand like how exactly we can do it. So suppose let B be in MNK. Okay. And since A1 to AD is a basis of MNK, again there exists Ci in K such that since B is in MNK, then B transpose is also in MNK, right? So for this B transpose, I can write this like linear combination of C1 to AI. And when we take transpose, so taking transpose, so I will have B is equal to B transpose transpose, right? And what is B transpose? It is summation I from 1 to D Ci AI whole transpose and AI the whole transpose, and this will give me summation I from 1 to D Ci AI transpose. Okay, so basically what so basically we also know how this AI transpose span the given vector space. Span span the given vector space. Hence this B is a linear combination of this A1 transpose to AD transpose. So hence this spans AD transpose MNK. Okay, and now that we know that it is also linearly independent set and we know it's also spans. So for any given B, I can write B in terms of linear combination of this A1 AITs, I mean AI transpose. So hence this A1 transpose to AD transpose is a basis of MNK. So this was one direction. Okay, so what we proved here was, so this is one direction, that if A1 to AD is K basis, so we are asked to prove if and only if statement. So this was one direction, that A1 to AD is a K basis, then their transpose will form a K basis. And now the reverse part. So, but I think you can, I mean, it will follow the same argument. But let me just quickly go through it. I won't be explaining much for this. Yeah. So assume we are assuming, since we are in converse, we have this A1 to AD transpose is a basis K. And again, linear independence. We will do the similar kind of technique or whatever you follow, linear independence. Suppose summation Ci AI is 0 to show. So we have to show that this A1 to AD is a basis of MNK. Okay, so Ci AI, we are assuming it to be 0. And now taking transpose, we get that summation Ci AI transpose whole transpose is a 0. And then this will be again, okay, let me write this, I from 1 to D. I from 1 to D, Ci AI transpose will be 0. So this will imply that, again, but this A1 to this transpose, AD transpose is a basis. This implies that Ci is a 0 for all 1 to D. And so this implies that AI is linearly independent set. So let me write, hence summation Ci AI from 1 to D is equal to 0 implies Ci is 0 for all. Hence, this set is linearly independent. I hope my handwriting is fine and readable. And similarly, the spanning, we will again take a matrix, take its transpose, and we will continue. Okay, so somebody, okay. Again, the spanning part, quickly we will go. Let B belongs to MNK, and so B is equal to summation Ci AI transpose I from 1 to D, as A1 transpose to AD transpose is a basis of MNK implies this. And so now taking again transpose, then B transpose will be summation, I don't understand, okay, I from 1 to D Ci AI power transpose will be summation I from 1 to D Ci AI transpose, that is summation I from 1 to D Ci AI. Okay, sorry for that. Yeah. I think we have to take transpose of this. This, so B transpose, this will be, since B transpose belongs to M and K, and then this B will be B transpose transpose, and then now I understood why they didn't take too many transposes here. Yeah, but at the end we got it right. I mean, B transpose is this, which transpose which we take, and now we have, yeah. So this implies that B is summation I from 1 to D. Let me write it properly. This implies that B is summation I from 1 to D, CIAI. Okay, so we got B as a linear combination of AIs. So hence this A1 to AI, AD spans M and K. Thus, A1 to AD is a basis of M and K. So this was one way to understand this question, where what we did was we actually tried to do the linear independence and this completely using the transpose of the matrix. But we can also do, I mean, this what we did here. Okay, so uh, let me just write it here quickly. That we did this, right? This CI AI is equal to 0 and so on. So instead of that, we can also try to do this, that this is summation AI, this AIJ, and not IJ, let me write A, or let me write this as CT, no, not T, CIA will be STT, no, I don't want to take T. Okay, let me take this as the alpha, and this as AIJ, alpha, and alpha from 1 to D, suppose, and its transpose is a 0. So each Aij is a 0, the entry wise. So if I take each entry wise, I mean, what I'm trying to say is instead of looking at the whole matrix, we can also look at it as each entry of that matrix. If this is 0, then this C1, A1, and alpha n, so on, Cn, I mean, CD, AI, D, so on will be 0. And the transpose will always give me the linear combination of again those same elements, which will be 0. So instead of looking at the whole matrix, we can also look at it at coefficient. So what I'm saying is it is matrix like this. The linear combination will give me some linear combination here at each entry. This will be 0 in original case. And when we take transpose, though this one will be transfer, so this one will go here, and this one will, I mean, this one will remain as it is. But it at the end remains the same linear combination of AIJs, and that still remains a 0. That's what I'm trying to say here. So look at it at, we can also, so what I'm saying is we can look at this proof as entry-wise combination, which is anyway 0, which is 0, which would be 0 uh, in the given assumption. Okay, so yeah, that's what I wanted to say. So yes, and yeah, so any doubts here? Please let me know. Otherwise, we can move to next question. Was this too confusing? I hope not. Okay, it's okay, right? I mean, uh, this aij one something like that. If we do, I mean, I'm just trying to do this. This is C1 aij. Again, this will be D. If this is 0, then this C1 A11 plus and 1 at the top, and C1 1D at the top will be 0. And this I mean, every entry, this C1AIJ1, when I write this one, this is AIJth entry of A1, okay? And so on up to this this will be CD, AIJ, D will be 0. And even if I take transpose, this will remain same. I mean, in transpose, this will be what I'm saying, that in the transpose, this will be my C. In transpose, this will be C1AJI1 plus CAJI. D will be 0, and corresponding entries will be 0 if I look at the entry wise, whatever it is. So this at the end will be 0. That's what I'm trying to say here. Sorry if that made you confused, but you can try to do this with 2 cross 2 matrix and you can understand that this is what is happening. Okay, so let us move to next question now. That for the following k-linear maps, if there are any doubts, please let me know. I will try to explain it. Find the matrix this MBBF in MNN. Okay, so MNNK of F with respect to the basis B is equal to Ti. I is from natural number of the polynomial algebra KT. So please don't be confused with the term polynomial algebra. It's just polynomial ring. Okay, understand it as a polynomial ring. Sorry. And these are the maps. F from KT to KT, and such that XT. So XT, don't be confused. It is just the way they have expressed the polynomial. So XT to XT going to X dot T. So X dot T is just a different derivative with respect to T. Okay, and second F is from again KT to KT. I will explain what this means. The matrix which they have asked us to calculate, and from B to B, what this B to B means. Okay, but yeah, for now, what the question is, yeah. So XT goes to XT YT, or YT XT does not matter since we are in polynomials, where this YT, yeah, I mean, they are writing YT in the first because they are treating it as a constant. So this is A naught plus A n t power n is a fixed polynomial. So why they wrote it as YT is like when we go if F is from R to R, it's like X going to 2X. This 2 is my Y here. So they want to treat this Y as some constant term constant element in terms of this map. And the C is F from KT to KT again. such that xt is going to xt plus 1. Okay, so let us understand what this MVB and what this means. Okay, first of all, they have asked us to find this MVB of this F. This F is a linear transformation. Okay, so what does this mean? And here they have written this BB, but what it means in general. So matrix of linear transformation. Okay, so what it means and why it carries a significance. Okay, so see, if we have some linear transformation T from V to W, okay, both are finite, infinite dimension, we do not care, but it has some basis. Okay, so I have this T from V to W. V has basis. V has basis beta. Basis of V is beta, and basis of W is suppose gamma. Then this T beta gamma is a is called a linear transformation matrix. Okay, is a linear transformation matrix. And what it has is, it has all these kind of entries, beta gamma. So it contains all these T of beta, T of beta 1, T of beta 2. Suppose, okay, so suppose assume it has this element beta 1 to beta n, and this has elements beta 1 to beta m. Oh, not beta gamma, gamma 1 to gamma m. Okay, so this will have all these beta 1 to beta n entries. And what it means is, but this each beta 1, I will write them as linear combination of gamma n, right? Because it is a basis. So see, any element V from this V will be some linear combination of beta 1 to beta n, and its image, which is element of W, will be again a linear combination of elements of gamma 1 to gamma n, okay, which is basis of my W. Um, if this is, I hope you are understanding, these are elements from V and W, or if these betas are confusing, please tell me that these betas are not confusing. Okay, this, I mean, this V is some A1 beta 1 A n beta n, okay, in general, and W is B1 gamma 1 plus Bn gamma n. So this matrix is actually this, and what it does is, we will see in examples that what exactly it does. Okay, so this matrix is now, so my this T beta 1 is a basis, it is some element, we do not care what it is, but T beta 1, whatever it will be, I will be able to write it as some element of A11 A B, yeah, it will be A11 gamma 1 plus A12 gamma 2, so on up to A1 n gamma n, right? So these entries will be A11, A12, so on A1n. Okay. Similarly, for beta 2, I will be able to write it as A21 gamma 1, A22 gamma 2, A22 gamma n, and so on. So this will be A21, A22, and A2n gamma n, and so on. So whatever we are getting here is expression of elements of image in terms of gamma n. Once we give one example, you will understand what this significance means. So what it does is, when I take some, so this is matrix, right? This is a matrix. So when I take some element here, this T, okay? And when I multiply this element a1 to an, so understand this T will be n cross m matrix, right? No, this is m cross n matrix. M cross n matrix, right? So this T beta to gamma, when I multiply some vector here, it will be some, suppose a1 to a, I think n, yeah. It will give me some b1 to bm, right? And what it is, whatever it is, so it, what it does is, this element here, this is actually a1 beta 1 plus an beta n, and it gives me image in terms of b1 gamma 1 plus bn gamma n, bm gamma n. Okay, so that's what it does. So we get hold of the map T using this matrix. Oh, I don't know what just happened. Okay, whatever. So that's what this linear transformation matrix does. Okay, it helps us to get the information about the map using any basis. We'll try to see this using example. And what I did here, all this, let me just highlight this with this color. From here to here, try to do this with some example of 2 cross 2 map. I mean, R2 to R2, just choose two bases. I mean, we will do that, but for yourself, take a basis, see how its linear transformation matrix is, and evaluate it and see what whether what we are doing is giving us exactly what we want or not. Let us focus on question for now. So f from kt to kt, and sorry, such that this xt is going to x dot t, okay? And we have to find its matrix. So understand that we won't, so this will be infinite matrix, okay? That's why they did not write here only m and r, okay? So these notations also really make sense. We need to put what we say. Uh, we have to notice how the notations are given. In general, when we write any square matrix, we simply write M and R, okay? Like you don't see someone write 2 to K or R, okay? They simply write M to R or M and R when N is finite, okay? But this, even though this looks like some square matrix, M, N, and R, but this is quite different thing, okay? It's like both the rows and columns are infinite, and I hope you know it won't be precisely a square matrix. It might look like a square matrix, but it not. This notation here actually carries some meaning, okay? Think about it. Okay, let us move to the question. Yeah, so how to find this? So as I said, we start with the basis, we evaluate basis, and we enter the coefficient of the basis as a columns in that matrix, and that's what we will be doing. So my basis B here is this t power I, such that I belongs to, sorry, I belongs to n. This is my basis. Okay, so what is uh, f of t0, right? Constant is also there. Well, in polynomials, so constant is also there. T0 is that. So this f t0 will be f of 1, that is d by dt of 1, and that is 0. Okay, and so this 0 is just 0 times t times 0 plus 0 into t power n, and so on. So the first column of this matrix will be 0. So I am just for now writing this matrix here. So let us try to write, not, so this m b b of this f, the first column I'm just leaving it as it is, okay? And here also it is as. So first column is 0. Everything is 0, okay? For now. Now f of t power 1. So d by dt of t, that is 1. So what this is? 1 plus, so 1 into t power 0 plus 0 into t power 1 plus, yeah, 0 into t square and so on. So now I will again align them in the second column, right? This is my f of t power 0. This is f of t power 1. And this is 1, right? And then rest are all zeros. Now second, f of t square. What will be? It is d by dt of t square, which is 2t. So, but what is 2t? 2t is 1, that is 0 into t power 0 plus 2 into t power 1 plus 0 into t square plus and so on. So this f of, let me shift it here. This f of t square is giving me 0, the first entry of t power 0. Second is 2. Then I'm again getting 0 and so on 0. And in general, if I take any f t power I, okay, so it will be d by dt, t power I t power I minus 1. So this will be what? This will be 0 t power 0, so on up to 0 t power I minus 2 plus 1 plus I, okay? It is I into t power I minus 1 plus again 0 t power I and so on. So it is like, if I look at this diagonal, the 0 diagonal in the middle, above this diagonal, I have I. For example, yeah, in the ith column, the it is like this. This matrix M B B T is Aij such that AI I minus 1, right? Is 0. Sorry, is I or I minus 1. I minus 1 is I minus 1 and 0 otherwise. Aij is I minus 1 if I is equal to, how to write this? Yeah. So they have written, so it is Mij, this MBB of F is Mij is J if J is I plus 1. We'll see what does this mean, and such that J greater than equal to 1 and 0 otherwise. So Mij, so this is J. So M and J must be I plus 1. So my A11 entry here or M11 entry will be 0, right? Because here J is not equal to I plus 1. But M12, sorry, M12. So this is first column, 2 row. So this, is this correct? Yeah. first row, second column. First row, second column is 1. I think it should be I. Now it is J. J will be my 2, right? It should be I here. But that's what I want. Then it will be 1. M12 is 1 here. Let us try to do this for this entry, right? This entry is 3, 2, like 2, 3. So M23 is 2, that is I, where J is I plus 2. Yeah, so it is this kind of matrix. Mij. Is this okay? And it's 0 otherwise. So it is called a super diagonal matrix with entries uh 1, 2, 3, 4. Super diagonal means element just above the diagonal. So this matrix MBB of F is of this kind. 0 in the first column, then first 0, then 0, 2, and then again this is diagonal. This is my diagonal. If I have this, everything will be 0. And for ith column, everything will be 0. Just above I, it will be and 0 and 0, so on. This is ith column. I hope this is understandable. And this is what I'm saying. This is my infinite matrix. So this continues for any given, for any given n, this happens. So any doubts here how this matrix looks like?
Ma'am, could you
Yes.
explain the bit where you said you changed J to I, right?
Yes,
Earlier.
yes.
Could you just explain that again?
Yes, so see, what I was saying is, see here what this entry is. This is my M one tooth entry, right? And I want it to be 1. This is my M two third entry, right? Second row, third column. I want it to be 2. That's how our matrix looks like. So we know how the matrix looks like, but now I want to write it in the compact form of this kind. And I wanted it to be 2, okay? And this M 3, 4, I want it to be 3 here, right? It will be 3 here and then 0. So, so to make sense of that, so here so this, if I write this as Mij, so this becomes I when my J is I plus 1. That's how it is. And I wrote here J, which is wrong. J is what? My 2, but that's not the entry which I want here. You understand? It was kind of typo or something like that. It was not correct.
Yeah, understood, ma'am. Thank you, ma'am.
Okay, okay. Is it clear? I hope you understood. I wrote it J, but that was not correct. So that's why I corrected it to I, because that's what we want. That's what we need here. Yeah. And rest all the entries are 0 because that's how the basis. So this is what we got. And yes, and this is infinite matrix. That's why we have to write it in this form here where I comma j are in n. Okay, so this is how the linear transformation matrix looks like for this uh, linear transformation. Now let us move to the next one. Okay, and what is it? Where is it? What was the second? Yeah, it is yt, multiplication by y. And again, we have to do the same thing. So for B part, it was f from kt to kt, such that x of t is going to yt xt, and they have given explicit expression for y such that y of t is a naught plus a1t. I hope that was the expression. Yeah, plus a and t power n. Okay, and yes, so again, my basis b is t power I such that I belongs to n. And again, to find the matrix, I again have to evaluate each element of a basis using this f, and whatever we get, we have to arrange the coefficients in the column. So then this f of, so this is 1 t, t square, t cube, and so on. I hope you understood this, okay? So f of 1 is what? 1 into y of t. So this will just be y of t, which is a naught plus a1t plus a n t power n, and so on. So if I want to write my, let me write this m b b f, the first column with respect to f of 1 is a naught, right? a1, a2, and then an. And note that this is infinite basis. So after this, it is t power n 0, t power n plus 1. Okay, so it goes till an, and after that, it becomes 0. I hope this is clear because my basis is infinite. It is for any n. And now the second one, MBB, not, this is not MBB. Oh, sorry. Yeah. This is, and now f of t. F of t will be, again, this y of t, which is a naught plus a1t plus a n t power n into t. And what this will give me, a naught t plus a1 t square plus a n t power n plus 1. So if I want to write it in terms of the basis, it is 0 into 1. Okay, I'm writing 1 instead of t power 0 plus a naught t plus a1 t square plus a n t power n plus 1 plus, now again this is 0 t power n plus 2. This is what we are getting. So for first one, so this is my 1 coefficient of 1, this is coefficient of t, this is coefficient of t square, and so on. So here coefficient of 1 is 0. This is my f of t. Coefficient of t is a naught. Coefficient of t square is now a1. Similarly, coefficient of t power n will be a n minus 1. So here in this row it will be a n minus 1. Here it will be a n, because this was what? This was corresponding to tn. This was corresponding to tn plus 1. And again 0. Rest is a 0. So it is, and you can now see that for any t power n, f t power I, let me write, it will be this a naught plus a1t plus a n t power n and t power I, and it just adds t power I to it. So this is a naught t power I plus a1 t power I plus 1 plus a n t power I plus n, so on. And if I want to write it as a coefficient of the basis, this will be 0 into 1 plus 0 t so on up to 0 t power I minus 1 plus a naught t power I, and the thing continues. And okay, let me write a few more terms. I plus n plus, now 0 t I plus n plus 1, and so on, and rest are all zeros. So it is like in ith column, f of t power I, it is 0 everywhere. And the moment it goes to I, it becomes A naught. So if my AI is somewhere here, AI, it becomes A naught. Suppose this is my, let me just write it here. This is my t power I coefficient. So this becomes A naught plus 1. Sorry, it becomes A1, so on. This becomes AN. This will be my coefficient corresponding to I plus N, t power I plus N, and 0. So how it looks like, this matrix is this. This is A naught, A1, AN, then shifting by 1, A naught, A1, shifting by 1. It becomes 0 and 0 rest. So you do you understand this, how it is? So it is just block of all these, this is patch of this AIs here, A1 here, AN here, and rest above and belows are all zeros. Is that okay? How this matrix looks like here?
Ma'am,
Yes.
here we are not taking like f of 0, f of 1, f of 2 like the previous question.
No, we are
Like,
doing that.
oh, we just use t as a placeholder.
No, I'm not getting you. What are you trying to say here? Um, which one? I'm really trying to understand what was the question. So here we did that. Instead of t power 0, I am writing 1 here. That's it. This is t power 1, this is t power 2, this is t power I. And that's what even we are doing. This is my f of t power 0. And that's what we are doing. T power 1, t power 2.
Oh,
Uh,
okay, ma'am. I got it. I was confused,
Yeah,
ma'am.
yeah, yeah, yeah. I think it's because that's why when I wrote this, after that I wrote this here, that this nothing but 1t square and so on. Yeah, so this was ft power 0. We did the exact same thing. We calculated ft power 0, ft power 1, ft square, ft power I to get hold of how it looks in general. Similarly, ft power 0 and ft power, this is ft power 1 and this is ft power I, and we got what it looks like. Okay, so it is like each column this there will be n entries which are coefficients of this y. So if I want to write again it in compact form like this, let me write this. If I want to write this in compact form, it will be like this. Hopefully, just try to write this. This mbb f, it's not t, it's f. If I write this as mij, it will be what? It will be ai minus j. If Let us check. Okay, this is what I wrote when I calculated it, and it will be 0 otherwise. And what does this mean? So my A11, no, yeah, A11, it starts with 0. So they are considering it as a 0 column. I mean, I got confused myself. So A minus J. So this is 0, 0. So A11 entry, yeah. So right, A11 entry is A1 minus 1, that is A0, that is true. Second, A21 entry is A2 minus 1, that is A1, and that's true, right? And we have to go till AN. So yeah, AN1 is AN minus 1, that is okay. Or maybe we have to add plus 1 here. Or no, let us check. This is become AN plus 1. Yeah, we have to go till n plus 1. Oh, but now no, they are not saying that it. Okay, this is correct. This is correct. As long as a I minus j is less than equal to n. So yeah, a I minus j less than equal to so a n plus 1 minus 1. That is a n plus 1 minus 1 is less than equal to n. So that's why we still have here a n, and this is the case. And now for next one, a n plus 2 1, my so n plus 2 minus 1 is n plus 1, which is not less than n, so it becomes 0. So it gets into this otherwise condition. So it not, I mean, it properly captures all the conditions where it happens. For example, in second column, this is A21, right? This is A21, no, A22 entry. So A22 entry, it is A2 minus 2, that is 0. And for here, it will be n plus 2th row and second. So this is n plus 2, comma 2 will be an plus 2 minus 2. And this will be an. Okay, so this holds for every column. Okay, and the condition is not on I or j, but it is on I minus j. So note this here. This condition here is on I minus j and not I or j. Okay, so this is compact form of this. Let me just shrink this one. So you, okay, I hope you got the idea, like how it is. If there is any doubt, please let me know. Why we are writing this in compact form is because this is infinite matrix. We can't show each and every term. Or for example, if you were asked to calculate linear transformation matrix for some R3 to R3 map or R2 to R4 or R whatever Rn to Rm for some fixed Mn, we can explicitly give. I mean, even now we are giving the explicitly, but we can write that matrix here, like the box form of that matrix here. But since it is uh, matrix with infinite rows and columns, we are giving it the compact form of how each entry of that matrix look like. Okay. Is there any doubt? Please let me know. Otherwise, we can move to next one. Yeah, and yes. Any doubts? Let me write just for the sake of completion that this will be A naught, this will be A1, this will be AN for ith. Okay, so now third part. I think it was, the third one is, yeah, it was this f from kt to kt. And we will be doing same thing. T goes to, sorry, x of t goes to x of t plus 1. Okay, and again we will be doing the same thing. We will calculate my basis b again is this t power I such that I is in n, which is again 1t square. Okay, so again we have to calculate this f of t power 0, that is f of 1. And where does it go? Oh, this is x of t plus 1. And when I write this, x of t goes to x of t plus 1, it means if my polynomial is, if x of t is a naught plus a1t plus a1 t power n, then x of t plus 1 is, instead of t, I'm just putting t plus 1 here. Okay, this is what it means. This is an. Okay, this is what it means. So when I am writing f of 1, so there is no x here, right? I mean, this is what, this is f of 1 plus 0 into x plus n. I mean, this is something like this. And instead of, so t, and instead of t, I'm substituting now t plus 1. So this is 0 t plus 1 and so on. So it is essentially 1. So f of 1 here still remains 1. Okay, it is not changing. Any doubts here? That it is not really changing. Okay, for 1 it is not changing. And for next f of 1 now, f of t power 1. So this is going to t plus 1. So this is 1 plus 1 into t plus 0 into t square and so on. Now f of t square will be t plus 1 square. Okay. So now this is what? This is 1 plus 2t plus t square. So this is 1 into t power 0. That is just 1. I'm writing here. Plus 2t, 2 into t plus 1 into t square. So if I am to write this in matrix form, let me just write this here. If I'm trying to do all the entries here, MBVF, first one it is just 1, 0, 0, 0, and so on. Nothing really happening. Second one, it is 1, 1, and 0. For 2, it is 1, 2, 1, and then 0. Right? This is what is happening. I'm right, right? Or there are any mistakes here?
Ma'am, like when you do f of t to the power 1, I am a bit confused why it's only affecting the first two coefficients. Doesn't it mean you substitute wherever t is with t to the first power?
This t power 1 means only t, right?
Yes, ma'am.
Yeah,
And why is it like becoming 0 after the third one in the second entry? Like t square. Why is 8 to 0 over there?
because see, what is f of t? F of t is t plus 1, right? From the definition. And so if I want to write it as a coefficient in the basis form, so my basis is this. I'm just expressing it in terms of a basis. So this is 1 into 1 plus 1 into t, right? Plus this is 0 into t square, right? I mean, there will be nothing, I mean, t square does not exist here. There is no t square. So it will be 0 into t square and 0 into t cube and so on. I'm just expressing this. For example, if someone writes 5 is equal to 2 plus, I mean, it's not really good way. So suppose my polynomial p, give me some polynomial, okay? Suppose my polynomial in t is x plus x square plus 7x cube plus 100 x power 5 plus x power 9. Okay? Suppose this is my polynomial. And now, or t. I want it to be in t. Okay? This is my polynomial. And now I want to express it in terms of basis. Okay, so I have to take care of each element of basis. So here constant is not there. So it is 0 into 1 plus 1 into t plus 1 into t square plus 7 into t cube plus, now there is no power for 4 right here. There is no t power 4. So this will be 0 into t power 4 plus 100 into t power 5 plus 0 into t power 6, because there is no power of 0 here. Power of 6 here. 0 into t power 7 plus 0 into t power 8 plus, now t power 9 has coefficient, that is 1. So 1 into t power 9, and again for rest it is 0. So 0 into t power 10 and so on. So I am just expressing this polynomial in terms of elements from the basis. My basis has all the elements from 1t, t square and so on. And I am writing those as a coefficients here in the column. So corresponding, so here the basis is 1, t, t square, t cube and so on. Okay, so corresponding to 1, I have to enter an entry here. Okay, so let me use this. Corresponding to 1, whatever coefficient, and this was like, this is my f of 1, f of t square. Okay, and and this is my basis of, this is my basis. This is also my basis. Okay, so corresponding to 1 here, whatever is the coefficient in f of t square, I have to enter this at here. And for example, then when I am talking about at f of t square, which is simply, where is it? Yeah, which is simply 1 plus 2t plus t square. What will I enter at this uh, at at this entry in the matrix? The corresponding coefficient of t cube. It will be 0, right? Because there is no coefficient for t cube here. Is it okay?
Yes, ma'am. My confusion's clear, ma'am.
Yeah, okay. That's why we are, I mean, writing these extra zeros to understand. I mean, I wrote this for t also 0 because to make the entry here, for example, corresponding to t square in this column, what should I enter? It will be 0 because there is nothing else. For t cube also there is nothing else. Similarly for t square and so on. Okay. So I hope I am doing this correctly, right? There are no mistakes here. Or are there? Can anyone spot any mistake? What I'm doing is correct or not, the way I'm entering the entries? We're doing it fine, right? I assume we are doing it fine. Okay. If there are any mistakes, please let me know. But yeah, but for next t cube, we have to do it for t cube as well to get the idea. So f of t cube will be t plus 1 cube, right? So which is 1 plus 3t plus 3t square plus t cube, right? I mean, if we are just expanding, and as I said, this will be 1 into 1 plus 3 into t plus 3 into t square plus 1 into t cube plus 0 and so on. So for this here, I have now entry 1, 3, 3, 1 and 0 again. And note that for any given t power I, this f of t power I, it will be what? It will be t plus 1 power I, right? And how it is expressed? It is summation, I hope you know, this is summation uh, j from, let me write it, summation k from 0 to I, k, I choose k, t power k, right? This is how we write it. So every coefficient will be what? It will be For f of t power I, it will be I choose 1, no, I choose 0, which we are assuming to be 1 here. I choose 0 will be 1 into 1 plus I choose 1 t plus I choose 2 t square, and this I choose k t power k, so on. I choose I t power I. This is how it will be, right? So therefore the matrix here becomes, that's what we are getting here also. This is this is this is 3C2, this is 3C1. I mean, this is 3C0, 3C1, 3C2, and so on. Okay. So that's what we are getting everything. Why they have written like this? Yeah. Okay. Any doubts here? I hope I'm not making any mistake, because so see, if this is the matrix, if I only consider this much, if I only consider this much, how it looks like, okay? Because my if I consider only this much, why I'm getting, because I feel it will be transpose of this matrix. This becomes 1 1 0 0, 1 2 1 0, 1 3 3 1, right? And if I take a polynomial, suppose if I take my polynomial to be t itself, t will be what? 0 1 0 0. So we are in R3 to R3. So this is, so what I'm doing here is I'm just reducing the original power as f problem as f from R3, sorry, k t k. I mean, all the polynomials of degree less than equal to 3. I don't know how it is. Maybe something like this. This is bad notation, but yeah, if I take evaluate it with respect to t, so it will be 0 1 0 0, right? That will be my matrix, and if I multiply, this will be 1 1 0 0, which is t plus 1, which is correct, right? This is t plus 1. Yeah, so that's what I was saying. So when we do the matrix multiplication, the linear transformation matrix, I want to find image of something. So what I do is, so this is with respect to b to b, right? M b to b f. This is M b to b f. So if I want to find image of f here under this matrix, so for example, if I want to find what is f of t, so what I do is I express this t in terms of basis. So t is what? 0 1 plus 1 1 plus 2 1 and so on, something like this. And yeah, and this is what I get here. I just write the columns of coefficients as a column, and whatever I get corresponding to that b. So my basis again is 1 and t square here. So this is 1 plus t I am getting. So for example, if you want to check this with some non-trivial polynomial, so suppose my f, suppose I take my polynomial p to be x, since we are in R less than equal to power 3, suppose I take this as x plus x square. Okay, degree of a polynomial won't change, so it doesn't matter. Suppose x plus x square, so, or t plus t square. So this will be what? This will be 0 into 1 plus 1 into t plus 1 into t square plus 0 into t cube, right? So the corresponding matrix, so if I apply this MTB, which is 1, 0, 0, 0, 1, 1, 0, 0, 1, 2, 1, 0, 0, and 1, 3, 3, 1. And now I apply this on this matrix, 0, this column. Okay, so I'm trying to find image of this element. And what I get corresponding here is 2, 3, 1, and 0, right? This is what I'm getting. So what does this mean? This gives me 2 plus 3t square plus, I hope I multiplied this correctly. Yeah, 3t square plus final is t cube or t square. This was constant. Yeah, this is t and t square. And yeah, this is my image. Directly I got it. And now let us check whether this is the case or not. So if I apply f on t plus t square, this will be t plus 1 plus t plus 1 square. So this will be t plus 1 plus t square plus 2t plus 1. And this is what I am getting here. T square plus 3t plus 2. And this is exactly what I got here. So this is the significance of this linear transformation matrix, which we obtain for given linear transformation from one basis to another basis. And what that basis significance means, that we have to write these columns as a coefficient of a basis which we considered, and what we get here is the what we say coefficient of a basis in the codomain. Okay, if my basis was something different, whatever coefficient I got here, it would change. Okay, it won't be the similar. For example, if my basis here was t plus 1 and so on in the image set, for example, and here I got this 3 in second place, then it won't be just 3t, it will be 3 into t plus 1. And when I calculate the image under the original map, it will be whatever I get there will be corresponding to this t plus 1. I hope I'm making sense here. Okay, that's why this calculation of this matrix is important. And how exactly, I mean, I hope using this you understood like how this matrix is actually used and what is significance of this b to b here. Instead of this b here, if we had some different b, the things would be different. Okay, and in general, this matrix here is n choose I and k and 0 otherwise. I mean, I hope you understood. So in general, this matrix MBBT will be, we will do one example. I mean, even now you understood explicitly like what this matrix are doing, but still, in general, for this matrix, if I write this as MIJ, this is, I'm still not convinced, but yeah, this is J choose I, where, and we are doing this above. So this was what this was. This is 3-tooth entry, and this was 2 choose 1, right? We are starting with the 0. Please fix the index, but yeah, this is J choose I, where 0 less than equal to J less than equal to I less than equal to N, and 0 otherwise. When I say J less than I means we are talking about lower triangular matrix or upper triangular matrix. I choose J. For 2, it is to choose 1. Yeah, I less than equal to J. I hope you got the idea. It will be I less than equal to J or J less than equal to I. This will change nothing, just lower or upper triangular matrix. Just take care. We need, let me write this in, we need upper triangular matrix. Okay. And yes, so fix the IJs here. Okay, so I hope you got the idea, but how the matrix would look like. It will be just n choose I, n choose J, and so on. Yes, so let's go to next question. If there are any still doubts about this, how this matrix and everything looks like, please let me know. Otherwise, we will move to next question. And yes, this time we will do something different, okay? The similar matrix, similar thing, but we will see when both the matrices are different, how exactly everything changes. Okay, so question, I think this is, and we are very slow today, but okay. So we have to write down the matrix. We'll do it fast, okay? Of the linear map, f from R2 to R4. So here the basis would be different. So we will see explicitly ki how when the bases are different, the matrix looks different and so on. This is the map 3a1 plus 3a2, 2a1 minus a2, minus 5a1 plus 3a2, comma 4a1 minus 3a2. Okay. And yeah, so this is my map. And we have to do this with respect to the standard basis. We know standard basis E1, E2, E3, E4 of R2 and R4 and standard basis of R4. And we will see how the basis look like. And respectively, we will do this with respect to the basis 1, 2 and sorry 1, 1 and 1, 2 of R2 and the basis 1, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1 and 0, 0, 1, 0. So this will be of R4. This will be a bit calculation heavy, but we can do this. Yes. So our standard basis for R3 to R4, R2 is standard basis of R2 is just this 1, 0, 0, 1, and standard basis of R4 is this 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, sorry, not 1, 0. And yes, when we write the matrix, this linear transformation matrix, the what we say, the sequence in which we are taking the basis element also matters. Okay, we can't switch. For example, here, uh, instead of writing I mean, this is very simple case where the coefficients are not different. But yeah, if I switch the order of bases here, the matrix changes. Okay. Here, this is corresponding to 1 t, t square, and t cube. And here also the corresponding coefficients are in terms of 1 t, t square, and t cube. And you have to take care of everything in this order only. If you change the order of bases, um, the matrix would change, because yeah, this is very order heavy calculation when we look at the linear transformation matrix of given linear transformation. Yes. And now again we will do the same thing. Find the image and write it in terms of the basis. And since we have to do it with this one, so this is my E1, E2, and this, let me write this with different pen. This will again be my E1, E2, E3, E4, but in R4. So this f of 1, 0, I will calculate. That's what we have been doing, right? We calculate, we evaluate the function at basis elements and write them as a column. So that's what we will do. We will do f of 1, 0. So this is 3 into 1 plus 3 into 0, comma 2 into 1 minus 0, comma minus 5 into 1 plus 3 into 0, comma 4 into 1 minus 3 into 0. And this is giving me 3, 2, minus 5, and 4. Okay. And f of 0, 1 will be what? This is 0 into 1 plus 3 into, let me just look at the map. Okay. What is the map? Yeah. 3 into 0 plus 3 into 1, comma 2 into 0 minus 1, comma minus 5 into 0 plus 3 into 0. No, 3 into 1, comma 4 into 0 minus 3 into 1. This is my second. So this is 3 minus 1, 3 minus 3. Is this correct? Yeah, 3 minus 1. So this is my image, and if I want to write this in terms of linear combination of this EIs, so this will be 3E1 plus 2E2 plus minus 5E3 plus 4E4, right? I hope you understand. Or this I'm writing shorthand, but here since we have space, this is what? This is 3 into 1, 0, 0, 0 plus minus 1 into 0, 1, 0, 0 plus 3 into 0, 0, 1, 0 plus minus 3 into 0, 0, 0, 1, right? So this is my 3E1 minus 1E2, 3E3 plus minus 3E4, right? And when I write the matrix M, if I call this as basis beta and this gamma, this M, beta, gamma of my linear transformation F will be again, this will be F of E1, this will be F of E2, and corresponding here will be coefficients of E1, E2, E3, E4. Or let me write this in green color because this E1, E2, E3, E4 are different from this E1, E2s here. And just the coefficients here, since coefficient of E1 is 3 here, it will be 3. It will be, for 2 it is 2. For E3 it is minus 5. For E4 it is 4. And similarly here, for E2 it is 3, minus 1, 3, minus 3. That's it. This is what we got. And this is my matrix. Okay. Now we have to write this in terms of, this is my matrix with respect to this beta gammas. So now I have to do this. Now my beta is this one, 1, 1, 1, 2. And my second one is, let me call this V1, V2. And now itself I will call them. W1 is 1, 0, 0, 1. W2 is 0, 1, 1, 0. And I will skip few calculations if needed to save the time. 0, 0, 1, 0. And now again, I will find what f of this 1, 1. And f of 1, 1 is again, what is that map? Yeah, I believe. Oh yeah. This is 3 into 1 plus 3 into 1, comma 2 into 1. Let me copy paste the map. Sorry for this. Yeah, so this 2 into 1 minus 1, comma minus 5 into 1 plus 3 into 1, comma 4 into 1 minus 3 into 1. This is the image. And what will be its image? It will be 6, 1, minus 2, 1. Okay. This, and the second image is, it is 3 into 1 plus 3 into 2, 2 into 1 minus 2, comma minus 5 into 1 plus 3 into 2, comma 4 into 1 minus 3 into 2. And this will give me 9, 0, minus 6, minus 1, and 4, minus 2. Okay. And now I have to express this in terms of this W1, W2, W3, W4. And how to do that? So this, now we express f of 1, 1 and f of 1, 2 in terms of, in the linear combination of W12, W4. Okay, that is our goal. So what it means, I want to express this 6, 1 minus 2, 1. This will be equal to some C1, 1, 0, 0, 1 plus C2, 0, 1, 1, 0 plus C3, 0, 0, 1, 1 plus C4, 0, 0, 1, 0. Okay, and if I compare the coefficients, I get C1 is equal to 6, right? I hope I don't have to write, or let me write C1, comma C2, comma C1, C2, C3. Yeah, C2 plus C3 plus C4 plus, for C4, it is only C1 plus C3. This is what I have. So this gives me C1 is equal to 6, C2 is equal to 1. This C2 plus C3 plus C4 is equal to minus 2, and C1 plus C3 is equal to 1. But C1 plus C3 is equal to 1. This implies that 6 plus C3 is equal to 1. This implies C3 is equal to minus 5, right? And I have C3 is equal to minus 5 and C1 is equal to 1. This will give me, so this will imply C1 is 1, C3 is minus 5, plus C4 is equal to minus 2. And so this will imply my C4 is equal to This is minus 4 plus 4 minus 2 gives me 2. So this 6, 1 minus 2, 1 is C1, that is 6 W1 plus 1 W2 plus C3 is, what was C3? Minus 5 W3 plus 2 W4. This is my first one, and the second one is 901 minus 2. 901 minus 2. And see, this is again linear combination. This will be again, let me copy this. This will be similar, right? I'm taking this as some linear combination of C1 to C4. Now, please let me know if you don't know why I copy pasted this here. Any doubt? See, I wanted to express this as a linear combination of these four vectors, okay? Similarly, now I wanted to find the linear combination of this again in terms of these four vectors. So this does not change, okay? This is, instead of C1, I can just write D1 and nothing gonna change. And whatever the calculation I did here in second step is happening on the right hand side, which has nothing to do with this. And now I can simply compare them, and now I get again C1 is equal to 9, C2 is equal to 0, and again C2 plus C3 plus C4 as 1, and C1 plus C3 as minus 2. But C1 is 9, so 9 plus C3 is equal to minus 2. This implies C3 is equal to 7, right? If I'm making any, okay. Oh, it's going minus. Okay, so it will be minus 11. So C3 is minus 11. So this implies C2 is 0. C3 is minus 11 plus C4 is equal to 1. This implies C4 is equal to 12, right? So we got all the four. So this 9, 0, 1 minus 2 is what? 9W1 plus 0W2 plus C3 is minus 11W3 plus what? Plus 12W4. And that's it. So my this M beta gamma of this F will be just coefficients, these four coefficients. This 6, 1 minus 5, 2, 6, 1 minus 5, 2. And this will be 9, 0, minus 11 and 12. Okay. And if you want to check that whether this actually holds, what we can do is this. See, now we check that these two matrices actually serves the purpose. For example, my standard basis was 1 0 0 1. This one was 1 1 1 2, right? If I want to find image of 1 0 using this matrix, so let me call this matrix A and let me call this matrix B. Okay. So if I want to find the image of 1 0 using matrix A, this will simply be this first column, right? Because what I will do, I will multiply this by 1 0, and what I will get? It will be just first column every time. So the image of E1 is this first column. Okay. And image, if I want to find image of 1 1, it will be image using B, then it will be image of this whatever we have in this first column. So let us calculate image of 1 0 using this one and 1 1 using A. So what we do is we calculate f of 1 0 using b and not 1 0. Let us do it for 0 1. Okay, for simplicity. Okay, and um, uh, f of 1 2. Let us keep it 1 2 using a. I hope what this a and b means. We just wrote here. So for first one, basis was my b was 1 0 0 1. So this 1 2 here is 1 into e1, 1 into 1 0 plus 2 into 0 1, right? So what I will do is I will take this a. Where is it? I will copy this matrix A. Multiply this with what I have coefficients here, that is 1 and 2, and I will calculate this. What I get is 3 9, 2 minus 2 0, minus 5 plus 6, right? Minus 5 plus 6, that is 1. 4 minus 6, am I doing right? It is 4 minus 6 will be minus 2, and this is the image of E12 under this, right? This is image of F12. This is what I got directly. And how I got this directly is because this is nothing but this is in standard basis. So this is nothing but 9E1 plus 0E2, 9E1 plus 0E2 plus 1E3 plus minus 2E4. Okay, and that's why I got this directly here. We do not have to do any further calculation to understand this. But now when I do this for 1 0 using B, so how? So now my B is 1 1 and 1 2, and I express 0 1 in terms of these two elements. How it will be? This will be, yeah, minus 1 1 comma 1 plus 1 1 comma 2, right? Because this will give me 0. 1 minus 1 will be 1. So this is minus 1 1. And now I am calculating this using this matrix. I hope this is not confusing what I'm trying to do here. Okay, and this is now minus 1 1. And this will give me what? 6 minus 9, that is minus 6 plus 9, that is 3. This is minus 1, minus 5 minus 11, right? No, 5 minus 11, that is minus 6, minus 2 plus 12. And this looks 3 minus 1 minus 6 10. And what is image of F01? It is this. Okay, and what we got here is this, which is different. But what this means is that we have to, we are still yet to obtain the actual image. This is 3W1. So image of this 1 0 will be 3W1. So 3, what was my W1? 3 1 0 0 1 plus minus 1 into 0. I hope I am not changing the. Please tell me that what I calculated here is still correct. Okay, if it's wrong, then we won't get correct answer. Plus My C4 is 10. That 0, 0, 1, 0. And what is this? This is 3. That's it. Second one is -1. That is correct. Third one is -6. Third one is C. Third one is -1, -6 plus 10. And fourth one is 3 -6. So this is 3 -1. This becomes, what is it? -7. This is 3. And now this is -3. And that is the image, right? I see 3 -1, 3 -3. So that's what it means. So whatever column we get here is not directly the image of F under that when I directly evaluate the given. So for example, if this is V, this T of V is not actually T of W. It just gives me information about the coefficient which I have to evaluate in using the coefficients. I mean, sorry, the basis. This just gives me information about the coefficient in the basis of codomain. I hope you understood what we did here, okay? If there are any doubts, please let me know. And if it was fast, that also please let me know. We wanted to do so many things, but let's try to do this one, and then we can stop. We are over time, but let us do this quickly. I think this is question 4. And we have to just check whether this matrix is invertible or not. And the best way to do is just check the determinant, okay? Nothing else. So we just have to calculate the determinant of this matrix. Determinant of A. Check is invertible or not. If it is invertible, then determinant will be non-zero, okay? And the determinant will be 1, 4 minus 2, minus 3, 4 minus 6, plus 2, 2 minus 6. If I'm making many mistakes, please let me know. And this will be 2 minus 3 minus 2 plus 2 minus 4. And this will be 2 minus 2 plus 6 minus 8. And this is 0. So this matrix is not invertible, okay? This matrix is not invertible using determinant. But one more way to do this is obtain the row echelon form of this matrix. If we have a row that with all the entries 0, then the matrix is not invertible, okay? So there are two ways. So if you are asked in the exam, you can choose either way. If it's not expressed that what method to use, just a second, okay? Yeah, what method to use to conclude whether the given matrix is invertible or not. But yeah, but if it is asked to not to use, so if they specify that do not use the determinant method, then you have to go to row echelon form. Okay, given matrix, convert it into a row echelon form. Check whether if all the rows remain non-zero rows in row echelon form, then the matrix is invertible. If we get even a single row with zero entries, we are done. The matrix will not be invertible. And quickly we will do one more question of similar kind. This, I think, is question 5, that for which I think we did such kind of question a few weeks back. I don't remember exactly. The following, I think we did that, something like this we did a few weeks back, where we were checking the whether the matrix is, yeah, invertible or not. In this case, yeah, understood. When we were discussing the homogeneous and non-homogeneous system of linear equation, whether we have infinite solution or finite solution and unique solution kind of situation, yeah, there we say that a homogeneous system has infinitely many solutions. If a matrix is not invertible, that is determinant is zero. But if it is the determinant is non-zero, then only 0, 0, 0 will be the solution. Yeah, that is where we were discussing the invertibility of matrix. Similarly, in case of what we say, um, non-homogeneous system, there we say that the system will have unique solution if the matrix is invertible. But if the matrix is not invertible, sorry, yeah, not invertible, then there are two possibilities. Either uh, it has it might not have solution, and so on. So there were three cases in that case. Okay, leave that behind. We are here for which A in R the following matrices are invertible. Yeah, we'll just check that. And they are asking to compute the inverse of matrix, but we can just follow row echelon and for this matrix. Okay, we'll just do this for this one, and then we can stop. 1 1 minus 1 0 1 1, and then determinant of this matrix, let me call A, is what? This is 1 into 1 plus 1 plus 0 into whatever plus A into 1. So this becomes 2 plus A, right? So determinant of A is 2 plus A, right? I hope I'm correct. This is 1 plus 1, 2, 0, A is 1. Yeah. This is 2 plus A. And the matrix A is invertible if determinant of A is non-zero. That is 2 plus A is a non-zero. That is A is not equal to -2. So this is the only case when the determinant is invertible. For any A other than -2, this matrix will not be invertible. Okay? Any doubts here? There are many such questions. There are two more matrices given in the question. You can calculate. Just just calculate the determinant, equate it to 0. See what conditions we have on A. Okay, so there is possibility that we can have something like this. For example, there will be cases where we will have some polynomial like this, that A square plus 2A plus 3 is equal to 0 kind of situation. Okay. I mean, suppose the determinant of A becomes this. Then in that case, A will have maybe two possibilities, or A need not have any solution. Okay. For example, if for this, if A does not have any solution, then it becomes invertible for any given A and so on. So we have to check such conditions. Okay. So be more careful with what we get as a coefficient. And this does not, I mean, I'm just writing some random polynomial, okay? Uh, Please don't take this polynomial seriously. Yeah, so that's it. Uh, you just have to check for where the determinant is non-zero, and you can conclude whether the matrix is invertible or not. There are any questions about this matrix representation or anything which we did so far? If there are questions, please ask. Otherwise, we can stop because we are anyway over the time. And I hope the pace was okay and it was not too fast to understand. Yeah. If there are any questions, please ask. Otherwise, we can end, and you can always ask your questions in the discussion forum. Yeah. So, thank you. We'll meet next week.